All right, well, let's get started, and I have something I want you to think about over the weekend. I'm going to ask you again on Monday, but as we're moving along, I've been working, I think, in the more difficult chapters we've done so far, which is 5 and into 6. And we were doing some air resistance, and so I'm going to continue with that and do a few more examples from the air resistant. Maybe another circular one. There's kind of a neat one with an airplane on a tether that goes around that's got some nice insight. So I'll do a few of those, and so maybe the first half hour, 45, maybe a whole hour, we'll do that. Then we'll get started to Chapter 7. And so Chapter 7 and 8 tie together so closely, it's kind of hard to tell where 7 ends and 8 begins, and so I'll probably just kind of tie them all together and get to the grand finale of conservation of energy, which is what 7 and 8 are about. 7 and 8 are introduce you to kinetic energy, if you remember that from 1 and 2, gravitational potential energy, Hooke's law and springs, and elastic potential energy, and ultimately conservation of energy. I say all that because for a couple reasons. Number one, I think 7 and 8 go a little bit quicker, and so we can go a little bit quicker. I think they're a little bit easier than the ones we've done in the past, so maybe that's some good news, or maybe you haven't had any troubles with this so far, and if you haven't, that's probably good news, because you probably won't have any troubles with this one, and that means you'll go into the next test. And that's where I'm getting at. Your next test is scheduled from 2 weeks from today. It's right before the spring break, and if we go quickly, we can get there, we can have the test there, or we could put it off. And I'm not sure which is better, to put it off after the spring break or do it before the spring break. So let's see how far we get. I'm going to ask you again next week, maybe take a vote. I will say this, though. I do not think coming back Monday of spring break is a good time at all. So if it's after spring break, I'm thinking the Wednesday after spring break, not the Monday after the spring break, and then kind of do a review on that Monday. But anyways, you guys kind of think about that and let me know. Would you want to, kind of push through, get it done, take the test before we go to the spring break, or have the time during spring break to kind of catch up, to kind of study, but not the day we come back. We can use the Monday or the Sunday, even at the end of the spring break, to do the review, and then have the test on the Wednesday. All right. Well, you think about that. Like I said, on Monday I'll ask you that same question and maybe a show of hands, but we'll also have more information about how far we have gotten since then. If you remember, we did number 30. Number 30 is kind of where we left off. It was the first one with some air resistance, and I believe it was some kind of race car or something to that effect. Sports car, 1,200 kilograms, and the drag coefficient was proportional to the square of the speeds. And so what we did is we said, let's write this as 1/2 drag coefficient, density, area, v squared, and that would be the drag on it as the car was moving in this direction with a velocity v. And this one, just kind of jog your memory, because we want to expand on this one. This one is the simpler of the process, because this one just says, what is the initial acceleration? And so all you have to do is know these parameters. What is the drag coefficient? What is the density of the air? What is the cross-sectional area? What is the speed? When you do all that, you will get then that resistive force that we were talking about. Taking that resistive force, dividing it by the mass, is going to give you the acceleration. What makes the problem hard, though, is this a constant resistive force? No. So whatever acceleration you get right now, is it going to be the same a moment later? No, because the car changes its speed. So in this case, this sports car was going 100 kilometers per hour, if you recall, when it was shifted to neutral. And I forget the number that we actually got, but we got some number for the resistance. We divided it by the mass, and that gave us the acceleration. All right, and that was the acceleration at that moment. And so this 100 kilometers an hour all of a sudden becomes now 99, 98, 97, okay? And when you're going a little bit slower, let's say 97 instead of 100, then you have a different acceleration. So do you have a constant acceleration? No. And so if the question's a little bit harder, like not what is the acceleration right now, but how long will it take for its speed to be cut in half? How do you do it? Which is what I believe it's number 34 is all about. So next on my list is 34. I'll turn the page here, and it simply says this. Here's the problem. Consider an object in which the net force of resistance is proportional to the square of the speeds. Okay? So it's a vague description. Doesn't really say what it is at this point. So it could be this sports car as we had in number 30. They say a good example of this would be a speed skater racing on ice. Okay, so one example is a speed skater, sure. Another example is this sports car, and there are many other examples here. The speed skater I kind of like. Usually a car you don't just shift in neutral and come to a rest. But if you've ever watched a race on the ice, you know, they're racing as fast as they can, and when you finally finish that cross line, you just kind of put your hands on your knees here and try to catch your breath as you coast around the track. And so you literally are slowing down only because of the air resistance as you are moving through. And probably very little resistance with the skates on the ice. And so that is a good model. And so that's why it says. So let's change it then to a skater. So here we have this problem. And we have a speed skater who's got their skates. What do skates look like? Skates. How about that? All right. Best I can do here. All right. But the point here is there is a resistive force. And that resistive force is proportional to the square of the speed, is what it's saying. Now, this problem does say, take that to be some number k times the mass times the velocity squared. So there is the velocity squared again. And instead of describing it in terms of drag coefficient, density, and cross-section, the author just kind of crams that all together and puts it in front and says it's some number times the mass, okay? So don't let that bother you. Maybe you should have put the mass together with everything else and just called it one big number, but you can see it's going to make the equation work out a little bit nicer, okay? And so that's the resistive force here. And so what's going to happen is you have some initial speed, V0, traveling in that direction. And so that's the speed when the skater crosses the finish line. Here's the question. The question in this one says, where did it go? Skater speed. The skater crosses the finish line of a straight line race with a speed of V0 and then slows down by coasting on the skates. Show that the skater's speed at any function of time after crossing the finish line is given by this equation. And so the equation they say is velocity as a function of time then would be equal to the initial velocity divided by 1 plus k times the initial velocity multiplied by time. And so that would be the equation of motion. That would be the equation of the speed as the skater is slowing down. How do we get that? Well,
was that equation given?
Yeah, so that's given. And says show that it comes out to be that way. So these problems are a little bit easier when you know where you're supposed to get, right? As opposed to find it. So this is what we're trying to figure out. How did the author get that? How does that show up here with Newton's second law? And like I think I said last time, is these air resistance ones, usually the physics part of it is really simple. It's usually the math part of it that's a little more challenging here. And so let's set it up. I'll start with this. Step one, got a good physical picture of what's going on? Okay, we've got a certain speed. We're going to coast to a stop or some speed based on time. Velocity is a function of time, right? Free body diagram. All right, what forces are on this individual? We're really flying now here, right? Okay. And obviously, the one of interest is right there, the resistive force. Now, there are the others, that is, the ice is pushing up with a normal force, and there's gravity pushing down. So if you do a sum of the force in the y direction, you get the normal force up and mg down. But that equals 0. We're not going to be accelerating up and down. So although that's true, that's not really what's relevant here. It's the sum of the forces in the x direction. And so maybe I should pause as I get to step 3. So here's step 2, free body diagram. And so that's the physics part of it. And like I said, I don't think this is the overall challenging part. Got a good physical picture of what's going on? Draw the forces. Now write out the equations, and then step 4, solve the equations. And so writing out the y direction and solve it's not a big deal. Writing out the x direction is, because this sum of the forces in the x direction is minus r, right? It's the resistive force. It's in the negative direction. And according to our setup of our problem, kind of a continuation of something going quickly here, it's proportional to the velocity squared. So this should be then a minus kmv squared. And so solve that for velocity. How do you solve it? Okay, I heard a couple people say this. Cancel the m. I like that. Okay. This doesn't really answer my question. Because although technically I've got an equation that says v equals, doesn't do me much good because it doesn't A depend on v. It's a lot like in your math class if you had x cubed minus x equals 3. They say solve for x. All right. X cubed minus 3 equals x. Yeah, I did it right. I don't really think you've got the point of the problem here. You haven't solved explicitly for x. You can't really solve this and calculate x because you need x to get x, right? And that's kind of the problem here. This doesn't really answer the question. We can't really get velocity because to get velocity we need acceleration, but we can't get acceleration until we have velocity. So these are tied together. So in a lot of ways, we've got a lot more work to solve this equation for x. Here too, we have a lot more work. And maybe you can see it a little better if I write it this way. Minus kv squared. And then I should write then the acceleration as how it is related to velocity. So see, it has a velocity in there. And so knowing how those two terms have velocity, kind of like this one, we can then do some, in this case, some algebra to solve it, and in this case, some calculus to solve it. And so now I need to solve this one. And so this one, fortunately, it's not a real hard equation to solve, but certainly something we have not done in this class yet, and you've done a little bit, maybe not even too much. I'm not sure how much you've done in your calculus. How do you solve something like this? What's the key to this? Yeah, good. Separation of variables, somebody said. Get all the v's on one side and all the t's on the other. Because we needed then undo the derivative. When you undo the derivative, you're doing an integrate. Right? And so we need to have all variables involving v's on one side and all the variables involving a t on the other side. And so this is what we call technically a differential equation, although it's the simplest differential equation we could work with. So we don't have to have all those fancy formality stuff that you guys some of you are there, but you will be there soon in your Math 220 class, so your differential equations. So this one is a separation of variables. In other words, this is what I mean. If I put this k, or leave the k there, and move the dt to this side, and on this side of the equation, move the v over to there, I now have an equation that has v's on one side and t's on the other. And that's really what I wanted to show you here. I mean, like I said, the physics part of it isn't really too difficult here, writing it out and then writing the equation. But solving it is something that you might not be as familiar with. But now that you've seen it, now you're going to be experts at it. Because now, just integrate both sides. So I will take an integral of each side. And so if I integrate this, I have minus kt on this side. A little more thought, but what's the integral of this one? Okay, so you might want to think of this as v to a negative 2. How's that? Yeah, so negative 1 over v, right? Okay, now I'm not quite done, right? You wouldn't stop here. What am I missing? Right, plus the constant of integration. If we're an indefinite integral, somebody said the beginning speed to ending speed, which, okay, we could write it as a definite integral, but writing it as an indefinite integral, there's a constant of integration. And so I'm going to go ahead and put it, say, right there, some constant c. Do I need to do both sides? Right, we had this before, but, you know, technically there's a constant of integration on both sides, but you have a constant and another constant. You can combine those constants and just say it's one constant that you still don't know about yet. But as you read the math, you will hopefully find out what it is. And so that's where we're headed.
Would it be the V initial?
Oh, good question. Would it be V initial? Not this time. It has been in our easy cases. Okay? But as I tried to say back in our easy cases, don't just always assume the constant of integration is the initial velocity. Read it, set it up, think about it, and find out what it is. So let's see what it is in this case. All right, let's say at time equals 0. What are you looking at in terms of this equation? Well, that term is 0, and so you would just have your constant. What do you have over here? Well, I guess my velocity at that time would be called my initial velocity. So there is my mathematics that says, what is my constant? Is it the initial velocity? No. Now, is it related to the initial velocity? Oh, absolutely. It's got to be, right? It's part of, you know, the equation. It's part of the integral. So it's going to be connected to it. Just how is it connected? So in this case, the constant is the reciprocal, or negative the reciprocal of the initial velocity. All right. So knowing that, I can now take that and put it into here and go minus kt, and in place of c, I will put a minus 1 over v naught is equal to a minus 1 over v. Okay? And so that is the equation I have so far. Now, still maybe a long ways from this, but perhaps not if you're kind of looking forward. Here is what I need to solve for. So I've got to do some reciprocals and common denominator, but it looks like it's going to come out to that. So I guess I'll start by multiplying everything by -1 and just get rid of the negatives. Maybe the next thing to do is to take the reciprocal of both sides, because when I do it over here, I get what I'm after there. I get what is my velocity. Then over here, the reciprocal would be 1 over kt plus 1 over v naught. So again, got some algebra to do, but now maybe you can see we are getting really close to that. If I multiply top and bottom by v naught, I get a v naught in the numerator, and in the here down here I get a k v naught t and plus 1. And so sure enough, there it is, the exact same equation that they were asking me to get, and I can find the equation. Okay? And so there's probably the new piece, right? Separation of variables. Put the v's on one side, the t's on the other, and solve it. Okay? The physics part, hopefully it's the same. Well, maybe one more down these lines here. 31 is kind of the same basic idea. It's good to see this a second time. And so let's write it out again. Now this is a little different in the sense that instead of having an object go really fast and the resistance be proportional to the speed squared, this one's going to be going slower. And it's going to be going down, so there'll be another force of gravity involved here. Watch, read this one. This one says, a small spherical bead that has a mass of only 3 grams is released from rest at time equals to 0 in the top of a bottle of shampoo. Now, I don't know why we're dropping a little bead in a bottle of shampoo, but I think you can see that being small and light, it's going to be affected by the resistance of this shampoo. And the shampoo being a thick liquid, it's going to get hard to go through, and it's probably not going to be going very fast, right? It's always going to be going very slow, and hence the resistive forces, instead of being proportional to the speed squared, will be just proportional to the speed. And that's the point here. It even says here that the terminal speed, that is the fastest this speed is ever observed to go, is only 2 centimeters per second. And so let's talk about this word terminal speed here. That's why I wanted to pick this problem here. Find A, the value of the constant b in equation 6.2, and b, the time it takes for the bead to reach 63% of its terminal speed, and the value of the resistive force when it is at its terminal speed. Well, let's start with that word terminal speed here. Okay? So imagine, if you will, here's the bead, here's the bottle of shampoo. We're going to drop the bead into, and I don't know if they say from rest. Did I see from rest? I don't think they're dropping it from a height and then it goes plop into the shampoo. I think they're actually putting their fingers into the shampoo and releasing. A small spherical bead is released from rest. Okay, and so it would be a little harder if it fell through the air first and had an initial speed, but they're just saying, look, release it right at the top here. And so this initial speed is 0, and now it's going to go faster and faster and faster. Okay? And of course, as it is going down, there's going to be some resistive force. Step 1, did I get it? You got a good physical picture of what's going on here? Got the bead? We're going to release it from rest, right at the top of the shampoo, and then all of a sudden it's going to start to fall. Gravity's going to pull it down, but the soap's going to have some resistive force. Step 2, free body diagram. All right, what does that free body diagram look like? How many forces are on this? Yeah, there's just the 2. I heard somebody say, well, there's the weight pulling it down. Exactly, so that's what's making it go down. And what is stopping it from going down? Yeah, that's the resistive force, R. And in this case, we're going to call it BV, being that it's not going to go very fast, so it's going to be proportional to the velocity. So what's different is the equation, not the physical concept or the free body diagram. And so we'll write out the equation. And the equation will look a lot different than it did here, because we won't have a v squared, we'll only have a v, and we'll have a force of gravity here. But other than that, it's just a matter of write out the equation and solve it. And of course, we're going to have another differential equation. We're going to have to do a separation of variables. We're going to have to integrate it, and we're going to solve it. But that's what I wanted you to see a second time. Yeah.
Do they give you BV, or are you supposed to figure that out?
Well, they say that it has a resistive force according to equation 6.2, and that is equation 6.2. So, yeah, they do give you.
R equals BV.
Yeah. So this was the resistance for slow objects. This was the resistive for fast objects. So that was equation 6.2. That was 6.3. So they did indirectly tell you, or even directly tell you, use the slower speeds. That's why they've got the little bead in the thick shampoo. Yeah. Okay. All right. So, got the physics done, right? Step 1, step 2. Physical picture, what's going on? Free body diagram. Now let's write out the equations and solve this. But I'll start with that concept. They keep using this word terminal speed, and I didn't use it. I think you're used to it already, though, and we saw it in the 102. What do we mean by terminal speed here? Before we had air resistance, we just dropped an object, and it would always go faster by 9.8 meters per second every second, right? Until it just went faster and faster and faster and faster. With resistance, is that what happens? No, what's going to happen here eventually?
It's going to equal the resistance.
What's going to equal the resistance? Yeah, and so hopefully you see when you first drop it, you don't have any speed, and you have weight, and so that pulls it down. Once it starts moving, and just for the sake of discussion, let's say pulling it down is 10, okay? So you're pulling down with 10. When you start moving, you might have a resistance of only 1 or 2. Well, then you have more force down than the resistive, so it still goes faster. But as it goes faster, you get more resistive force, right? And so that resistive force becomes a 3, a 4, or a 5. But even at 5, you still have the 10 pulling you down, but only 5 pulling you back. So don't you still go faster? Well, then as you go even faster, this becomes a 6, 7, 8. And what happens when it eventually becomes a 10? What happens when this pulling down as a 10 is equal to this pushing up, which is a 10? Yeah, now your net force is 0, so your acceleration is 0, and you won't go any faster. And so as you fall, you have come to a maximum speed, and hence the name terminal speed. You won't go any faster than that. Raindrops are great examples of that. They start at 10,000 feet, and they don't go faster and faster, like 10 meters a second or 9.8 meters a second every second. If they did, they would be coming down so fast they would kill everything living down here on the earth. So they do have some resistive, and then how much of that is in connection to their weight, and then how fast they come down. You've probably noticed that. I mean, we get this Santa Barbara mist coming down in the morning. You can those things are barely falling. Their rate is so slow that just walking through it stirs them around here. When the rains actually come, the little drops, you can actually see them come a little faster. Their terminal speed is a little bit greater. In those rare occasions where we have the big thunderstorms and the big droplets, they have coming down with a larger terminal speed. Fortunately, not enough to kill anybody, but they come down pretty fast, and nobody likes to be in the rain at that point, being pelted. It's a very different value of the terminal speed. But if you didn't catch that, that was the idea of the terminal speed. So the terminal speed would occur then when the resistive force equals the force of gravity. Now I say that because I think that was question C. Let's read question C again. What is the value of the resistive force when the bead has reached terminal speed? That's an easy one, right? I'll do this first. What is the value of the resistive force then? It's equal to its weight, right? Right, so it is going to be, the resistive force is going to equal to mg. Now, if you wanted to put it in newtons, which we probably should here, the 3-gram bead becomes 0.003 kilograms times the 9.8 meters per second squared there. And so that's the concept of the terminal speed, and makes calculating that value pretty simple. And we are looking at 29.0294 newtons. And so there is the resistive force. At that point, the force pulling it down, gravity, which doesn't change as it goes down, is the same as the resistive force. So the resistive force has built up to that value. Now, before it gets up to that value, so back here, then it is going lower than its terminal speed, though the resistive force is less than its weight, and it does have an acceleration. And we should be able to solve then for that equation, and what is that acceleration? So let's write that out. Let's write out the sum of the forces, and I might as well do the y direction. Although I guess I do have a question for you. Which way shall we call positive y? There are a couple say down, a couple say upward. The upward, probably that's the way we've always done it. The downward, because isn't that where everything moves, is down? And I think I'll go ahead and do the down as positive. I know it's a little bit off the traditional way of up positive, but it's what your author does. So as you look at your notes and as you do the reading, they'll match, and I think you'll have an easier time of understanding it as you study for the test. Okay, and so you can look at that. So he calls down positive. So keeping that in mind, then the force of gravity, mg, becomes a positive number because down is positive. Whereas the resistive force, minus bv, becomes a negative number because it's up, and that's the negative direction. And what does that have to equal? Yeah, ma, right? And now we're back to this problem again. I guess I've kind of erased it here, but can you solve that equation for velocity? Now again, I don't mean just move this to the other side and divide by the b, because then we would get some equation that I guess looks something like this: ma minus mg over a negative b. Although technically true, not very useful, just like back here. It's got a problem in the sense that good luck figuring out what v is, because to get v you need to know acceleration, but to get acceleration I need to know v. So it's not a good solution. You have not explicitly solved it for velocity as a function of time. So like I said, although not technically incorrect, really not what the intent here is. Could we do it better? Absolutely. But now, to do that, we'll do like we did before. We've got the mg minus the bv equals the m, and then let's write this as dv dt. Okay? And so now we're back to the same type of problem, which, as I wanted to show you, is not too hard, but you need to see it the first time. It's a mathematical equation. How are you going to solve this? Well, you have a derivative. Well, you're going to take an integral. But to do the integral, we need to make sure our variables are on the opposite sides. We call this separation of variables, at least for the easiest type of differential equation. So this one, though, I must say, is a little harder than this one. This one was real easy to separate the variables. I just had a v over here, and I divided it. What am I going to do there?
Get the v on this side.
Okay, I'm going to get the v on that side. Sure. How? If you add it to both sides, it doesn't help. You get an mg, but the reason it doesn't help is you don't really have the v with the dv, right? So how do I get the v with the dv? And again, technically not wrong, just not quite what I'm after here to show you. Okay, good. You guys see it here. So let's do this. I'll rewrite the equation. It's mg minus bv equals m dv dt. What if I were to do this? What if I were to divide by the whole thing? mg minus bv. What would I get? Well, I guess on this side of the equation, I get just a 1. On this side of the equation, I get an m divided by mg minus bv dv dt, right? Now, is it my v with my dv? And so that's kind of what I did over here. It just wasn't so hard looking because I didn't have two terms to deal with. Now, to get the t on the other side is not real hard. I'll just put the dt over to there, and I get an m over an mg minus bv equals dv. Now that, hopefully, is very solvable for you. So again, separation of variables on these simpler differential equations, one derivative, first derivative is what I mean, then do a separation of variables. Put all the v's on one side, all the t's on the other, or whatever your variables are, all the x's on one side and all the y's on the other side, and then do an integral with it. And so these are the type of differential equations that I know you've been exposed to in your calculus class. They're the simplest one. They're just kind of, hey, do an integral. You'll get acquainted with more later on, both in this class and in your math class. But for right now, this here is probably our most significant calculus we've done so far this semester. So now let's integrate both sides. And so now we can integrate. And so now we're back to our math class. And again, this is a little harder integral than the one we did before here. Not unreasonable, but certainly harder. This side is an easy one. Integration of dt is just t, right? I'll leave a little space to make sure that I add my constant of integration in there. So don't forget, I'm going to need a constant. And I can put it on left side or right side. Doesn't really matter here, but I got to do one side. And there's no point in doing both sides. All right. What's this one? Okay, m's a constant. Oh, fair enough. I'll pull that out in front. What's the integral of that one? Okay, good. You guys see it. I was wondering if I should do a substitution, a u substitution, and get a 1 over u, or not needed. You see it right away that it's going to be an ln of mg minus a bv. I mean, if you call u equal mg minus bv, that's kind of how we do these substitution or u substitution ones, then you would have an integral of u downstairs, and then if you do your differential, the du is a minus b dv, so dv becomes a du over a negative b, right? And then now you've got your du, which is your natural log. So you see that. So if you see that, then this is the minus b there for the the constant of the substitution here, the change of variables, the Jacobian, if I guess you want a fancier word there, as you change from one variable into another variable. Okay. So let's see what I have so far. I still have even more math to do. So like I said, I think this one involves a little more math. It's still separation of variables, but I think a little bit harder. Then it's an integral, which I think is a little bit harder. Then I've got some algebra, but I got a natural log, so I have to take an exponent. I have to undo the natural log. So I think that's a little bit harder. So I'm going to go ahead and bring the negative b over mt to this side of the equation. This is, I'm just going to still call it a constant because it's some constant, and all of a sudden now I'm going to multiply it by a b and I'm going to multiply it by an m. What am I going to get? Some constant that I still don't know anything about yet. Now I'm going to have to take some time to study it in a minute here, but let me just call it some other constant that I don't know. If it makes you feel any better, I can call that constant 1 and constant 2 to tell you they're different constants. Okay, but I still don't know anything about them. So there's no point in writing all those other pieces apart there. This then is the natural log of mg minus bv. I want to solve this for v, and in order to do that, I've got to undo the natural log, right? I got to take the anti-log. I got to raise it to a power of e. So this would be e to the minus bmt plus this constant. Now again, let's do some algebra over here. This is e to the minus bmt e to a constant. And there's no point in writing e to a constant, because what is e to a constant? Some other unknown constant. If you prefer, I'll call it C3, but it's just still some unknown value that I haven't quite studied and figured out yet, but I soon will. Rearranging this for v, would give me BV, when I move it to this side of the equation, equals to mg minus this C3e to the minus b over mt. Now I can divide by b, divide by b, divide by b, and finally I get close, other than I still got this constant to think about, but I get to my equation, what is the velocity of this bead as it is going down? And now I can say, well, how did we start off? At time equals to 0, what was the velocity? 0. So let's put that into here and see if that can give me some insight into what these constants are, and it will. I'll put in a 0 there for the speed. This will be an mg over b. This will be a minus a c3 over b. And this would be e to the 0. E to the 0 is, of course, 1. So when I move this to the other side, c3 over b is an mg over b. In other words, c3 is mg. Okay? Perfect. Because now putting that back into this equation gives me mg over b minus mg over b e to the minus b over mt, and then factoring out an mg over b becomes 1 minus e to the b over mt. Whew. And there it is. And like I said, I think probably the hardest part of these ones is the math part of it, not so much the physics part of it. So I, again, wrote out the equations based upon Newton's second law. And that's it. It's simple writing out the equation. Now it's solve that equation, and there is obviously a lot of math there between calculus and algebra in figuring out what the velocity is. Okay? And so that would be the equation for the velocity. If I made a plot of something like this, velocity versus time, well, what would it look like? Well, this would say it's an exponential decay, upside down, offset by 1. Right? And so that's what that graph looks like. And you can see then it's slowly approaching some constant value. That's what we said its terminal speed was. And so take a look at this. If you take the limit as time goes to infinity, what do you get for velocity? After a long period of time, what does e to the negative 10,000 billion give you? That's 0, right? And so the terminal speed is mg over b. Which I suppose if we wanted to just know its terminal speed, we could have done that back here. At its terminal speed, what did you say its acceleration was? 0. And so mg minus b at its terminal speed is equal to 0. So its terminal speed really just is the mg over b. So that would have been a much easier way to get the terminal speed. We wouldn't have to actually solve all the calculus. But that's not what I wanted to do. I wanted to solve it everywhere, not just at its terminal speed. So we did get an equation, and if we did take the limit as time goes to 0, we would get that terminal speed. Which is why we can answer the rest of these two questions then, now that we've done the math. The first question, A, says, find the constant b. Now they told us the terminal speed is 2 centimeters per second. So knowing that we have 2 centimeters, I'll write it as 0.02 meters per second, equals 0.003 kilograms times 9.8 meters per second squared divided by b, means that I can solve this for b, which is what the question is. So 0.003 times 9.8 divided by 0.02 coming up with 1.47. And let's see, I guess a meters per second would cancel off, and the unit would be a kilogram over a second. Would that make sense? Yes. And so kilogram per second would be the unit for this value of B. But there's the value of B, 1.47. And then B says the time at which the bead has got 63% of its terminal speed. Which sounds like a funny number, 63%. It actually says 63.2%. Why would anybody pick 63.2%? Seems like a weird number until you see something about the natural logarithms. Then you'll understand why the author is picking the 63.2%. Watch, let's set it up here. So here's the equation that I just solved. mg over b, e to the minus b over mt. They want to know when is it 63.2% of the terminal speed. Well, you can see the first part. Why did they label it in terms of the terminal speed? So that those two sides would cancel off, right? The mg and the b. And so that reduces it to a little simpler. 0.632 equals 1 minus e to the minus b over mt. Now you'll see why the author has picked the 63.2%. Because if I rearrange this to e to the minus b over mt equals 1 minus 0.632, I get my 37% or 36.8%. So, why 36.8? Well, because when you take e to a negative 1, you get 37%. Okay, so if I take the natural log of both sides, that natural log is a simple negative 1. Very common number in science and engineering. That's why they're called natural logarithms. They show up naturally a lot of times. So they have to do with all kinds of, in this case, resistive, how it is proportional to the speed. Anything where a change is proportional to the same value, like population growth, will show up as a natural logarithm. Okay? Oh, sorry. I think that was somebody was raising their hand there. Yeah. I forgot to drop the E there. And so that's why the author gave it. So, obviously he could have given like half the speed or something. And then we'd have to actually get our calculator out. But by saying it's 63%, we don't have to get our calculator out, at least not yet. And then so we've got minus b over mt is equal to the negative 1. So I'll cancel those off. And so time is the mass divided by b. The mass is 0.003 kilograms. And the b we just figured out a moment ago at 1.47 kilograms per second. So now I got to get my calculator out, but then that's going to give me the seconds. How many seconds does it take to get to the terminal speed? And hopefully not too much of a surprise, it's not long. It's not going very fast to get to its terminal speed. So it quickly speeds up and really doesn't go much faster than that. So we're looking at about 2 milliseconds, and it's dropping something in there. You really don't even see it accelerate. You just drop it, and it just looks like it starts going down at a constant speed, a lot like dropping a piece of paper or a feather. It just real quickly gets to its terminal speed, and But in this case, 2 milliseconds. It's not at its terminal speed. What is it, 63%? In fact, we never say when does it get to its terminal speed, because how much time does it really take to get to its terminal speed? It never does, right? It's an asymptotic equation here. It gets closer and closer and closer. You can say, how long does it take to get 90% of its terminal speed? How long does it take to get 99% of its terminal speed? How long before 99.9999% of its terminal speed? But you're never going to really get to its terminal speed here. So we don't say how long. That's why we like to use that magical, 37% or 63%. Yeah.
So on the two cases of the resistive forces, so at low speeds, use the lower bead, and there's no parts to that. It's just some one number constant.
Yeah, right.
And then at the higher speeds, the uppercase speed or whatever, that's made up of the drag, the density, and the cross section.
And cross section, right.
So is that because of how fast it's going, it has to push the stuff as well as go around or whatever?
Right. So at the low speeds, it's only proportional to v, because all you're trying to do is go around it, and so twice the speed means you go around twice as many molecules. But at a high speed, they're ricocheting off you. So when you go twice the speed, you hit twice as many more, and you hit them twice as hard. So you've got v and another v. Twice as many, twice as hard. Yeah. And so that's kind of the physics behind it. I don't think your author took the time really maybe to say too much about the physics, other than to say this is what it is, put it in the equation, solve the equation. So, and that's what I wanted to show you, solve the two equations. All right, well, maybe we'll do then one more. We did enough of air resistance. Let's just jump back to a circular one. Here's one, number 61, airplane going in a circle. It has some other neat little pieces here. So let's see if this makes sense to you. We did a bunch in a circle, but it's time to move into chapter 7 after we do this and say, all right, let's look at our energies here now that we've spent 2 weeks and a little bit more actually on Newton's second law. But I think by now you're getting the idea, and I know that you'll be working hard on them this Friday with Dawn and over the weekend and saying, all right, got a good physical picture of what's going on? Okay, draw the free body diagram, write out the equations, solve the equations. And so those will be your 4 steps, and half of it is physics and half of it is in the math. This one here says this. It says a model airplane has a mass of 0.75 kilograms and it flies with a speed of 35 meters per second in a horizontal circle at the end of a 60-meter control wire. Now that's a long wire, but it's a little toy airplane. If you've never seen these, in fact, they're really not as common as they used to be, because today's electronics and radio control are much more interesting, so people don't have these tethered ones. But if you can imagine this long wire on this airplane, the idea is kind of like flying a kite. You're tethered to the airplane, and it's reaching out, and if you're the operator of it, you're flying around like this. Your cable goes out to the airplane, and as you move the cables, you can control the fins on the airplane here, and it just kind of flies around in a circle here. And so kind of a view of this would look something like this. Here's somebody on the ground. They've got their arms stretched out with the control wire. The control wire goes out, and then here's the airplane. And then the airplane is making a circle. And I don't know if should I try to draw any ellipse in here so it looks like a circle, but it would be going, in this case, into the board and out of the board, something like this. So it would be going into the board and out of the board, something, yeah. But not up, down, right? This is in, should I leave that, erase it? Okay with that? Okay, so, but it's supposed to be this 3-dimensional thing. So there it is, going around, something like this. And they say this wire is 60 meters long. And they said the airplane had a mass of 0.75 kilograms. And so that's as much as we've read so far. Model airplane, mass 0.75 kilograms, flies with a speed of 35 meters per second. In a horizontal circle, at the end of a 60-meter control wire, compute the tension in the control wire, assuming that it makes about a 20-degree angle with the horizontal. Do not forget about the aerodynamic lift. Okay, so maybe we should talk a little bit more about that. We haven't done any problems with the aerodynamic lift. We haven't done Bernoulli's principle in this course, but why does an airplane fly? What did you learn in your Physics 102? Yeah, so it's that airfoil, right? You got the wings out here, and as it goes across here, the air flows over the top of the wing, right? And so that's going to make a low pressure here and a high pressure. So in other words, there's going to be an upward push on the wings. That's the aerodynamic lift. And so we'll keep that one in mind. Let me put the 20 degrees up here because they said, you know, go ahead and say that the control wire makes an angle of 20 degrees here. Well, maybe I'll pause right there because this is one you really want to take a lot of time. Do you got a good physical picture of what's going on? Right? Got an idea? Plane going in a circle? Horizontal circle, I should point out, right? Angles 20 degrees, cable 60 meters long, right? Flying 35 meters per second. Okay. Step 2, free body diagram. So if I take this little dot to be the airplane right there, what forces are on this airplane?
Gravity.
Okay, easy one probably is gravity. There it goes, mg. That's the one that doesn't touch it. Anything else touching it?
Tension.
Oh yeah, so we've got the tension in the control wire. There's T, which is the question, right? What is the tension in the control wire? Anything else? Yeah, this is the aerodynamic lift. This is the one that I warned you about. Don't forget the aerodynamic lift. Now, their picture is much nicer than mine. They make it pretty clear that the control wire is connected to the tip of the wing. So this airplane is flying like this. So which way is the aerodynamic lift? Yeah, perpendicular to the wings. So the aerodynamic lift, I'll put a little F here and put maybe some horizontal and vertical lines in here so you can see it. But there's the lift, if you will, is angled slightly in. Which is, if you've ever seen, like in the movies, a real airplane, I mean, what happens, it doesn't have a control wire on it, obviously, but in a real airplane, if you're flying along at a level flight, what would you know about the lift compared to its weight? They're equal, right? Now, if you wanted to turn to the right really quick, how could you do that? How would you get a force to the right that is going to make you turn? What do? Yeah, you now then tilt the wings because now this force, instead of going straight up, is now angled, and so you have a component that direction, and so all of a sudden now you turn to the right. But what else happens? What happens if you do that? Remember, the force lifting you up was just enough to overcome gravity. When you now tilt it sideways, how much upward force do you have? You have less now, don't you? And so what's going to happen to this plane? It's going to have a net force down. So yeah, so if you're flying along here and you tilt the wings, yeah, you're going to turn, but the turn is going to be a drop at the same time. You're going to be turning and falling now because you don't have that same amount of upward force that you had here. And that's, of course, kind of what we see here as we work on the problems. Of course, this one is not going down, so we're going to have enough upward to match our downward. Except our downward is not just the downward from the force of gravity, but it's also got this cable that's pulling it slightly down too. So certainly a much harder problem than any of the circular ones we've done before. But that's it. Those are only the forces, right? We've got the force of gravity, we got the cable touching it, and we got the air molecules touching, right? Those are the forces on it. So step 3, write out the equations. Now writing out the equations also means, what's your coordinate system? So what coordinate system do you want?
X is on T and Y is on F.
Okay, so now before I answer this, I gave you an important clue, and it's really important, or very useful, and not necessary, but going to make the problem a lot easier. Set up your axis so one of them is in the direction of the acceleration. Remember that discussion? Remember how that gives us an advantage? Because then one of the equations is equal to 0 and we don't have the sines and the cosines. So what is the direction of our acceleration? Is there any acceleration? It's going at a constant speed, right? So no acceleration? Ah, but it's turning. So yes, there is an acceleration. Don't let me fool you. All right, so it does have an acceleration. What direction is that acceleration? Where is it? And again, this is where more of the physics comes in, because if you don't get the physics right, the math is irrelevant at that point. Where's the center of the circle? Yeah, and so I'm hoping you see it. This is the center of the circle. Right? Center of the circle is not down towards the person holding it. Right? The airplane is up there. The airplane is going around in a horizontal circle. And so the acceleration needs to be towards the center of the circle. And we need to see that piece of the physics so we can set it up. And if we miss that, then there's really nothing we can do about it. Okay? Okay, and then we can write out the equations. Okay?
You can find the radius now.
Ah, good. Hang on that one, because that's another little subtlety I want to make sure everybody sees too when we get that far. All right? But got an idea now? So now I would agree with those of you who said, why don't we use the traditional coordinate system? Do not tilt it. I know our forces, some of our forces are tilting, and that's tempting to tilt your axis. But, and you can. I don't think that's better. I think it's better to leave it untilted. I think it's better to have a result so that acceleration, the radial acceleration, is along one of your axes. Because when I do that and I say, well, let's look at the sum of the forces in the x direction, what do I have? Well, what forces are in the x direction? Maybe I'll put some angles in here. If that cable is angled up at 20 degrees, then this is an alternate interior angle of two parallel lines. That's got to be. And this has to be perpendicular to it, the wing, so that is 20 degrees in there. So when I go to add up my forces in the x direction, I have an F sine of 20 degrees in the negative direction, don't I? Magnitude, component, direction. And if I go to add up my force in the x direction for the tension, it would be T cosine of 20 degrees in the negative direction. Okay? And so there is magnitude, component, direction. Again, notice how I used sine of 20 degrees here to get the x direction, but cosine of 20 degrees here to get the direction. Here I want the adjacent piece. Here I want the opposite piece. And so those two are in the x direction. Now this one doesn't have anything in the x direction, so I won't worry anything about that. And that has to equal to what? Okay, mass times the acceleration in the x direction, which the acceleration in the x direction is the centripetal acceleration. It's the v squared over r. That's why it was pointing for me to see where the circle was, where the center of the circle was. And in this case, the center of the circle is in the negative direction. And so I've got negatives in front of all of those, which I can now change to positives if I wanted to, or I could have just started by calling that the positive direction and only ended up with positive. So either way, same equation as it should be. Okay? And if I write out the other equation, which is the sum of the forces in the y direction, I would have F cosine of 20 degrees for how much of the lift, the aerodynamic lift, is in the vertical direction, and it's a positive direction, whereas the tension, the vertical component, is sine theta, and it's in the negative direction, as well as the weight is in the negative direction. And again, notice that for the aerodynamic lift, I want the adjacent piece, so it's cosine of 20, whereas for the tension, I want the component that is opposite of the 20 degrees. I want the downward, so it's sine of the 20. Okay? And so up, down, down equals what? 0, right? So that the plane is not accelerating up or down. It's going in a horizontal circle. Okay? Now I think I know all of these except for 3. Let's see. Do I know G? Yes. Do I know M? Yes. I know the angle? Yes. Do I know tension? No. That's one thing I'm looking for. Do I know F? No. Anything else? Do I know M? Yes. Do I know V? Yes. Do I know R? Yeah. So what's R? Yeah, it's not 60, is it, right? So there's another little subtlety hopefully you caught there. It is going around in a horizontal circle, and this is its radius, so it would be 60 cosine 20. So this is a 60 cosine of 20 degrees. This is the mass, 0.75. This is the speed, 35 squared. So I know all those. The F and the T I do not know. That I know. And 2 equations, 2 unknowns, and since it's 10 o'clock, I'll just stop there and say, I think you can solve the math the rest of the way. 2 equations, 2 unknowns, you can, and then you can solve it. Okay? And so those are our 2 chapters. So I'm not sure where you are. Hopefully you've been able to keep up with the pace of the class, and hopefully the busyness of the semester hasn't overwhelmed you yet. And if you are getting more than 6 hours of sleep, consider yourself lucky. But maybe you need more homework, or if you get more than 6, or if you played any video games within the last 3 weeks. So I'm not giving you enough homework. No, but I know this is the time in the semester things can get really busy. Don't let that happen to you. Especially after spring break, because I know how intense this class can get, and I know how intense your calculus class can get, and all your other classes. So it sounds like you guys are staying well on top of this. Good. And like I said, 5 and 6 go together. They're just Newton's 3 laws of motion, and I say just Newton's 3 laws of motion. But I know they can be a lot of work. But I'm hoping you see the bigger picture of the physics, and the physics is just that. A few fundamental ideas explain a universe of phenomena, and those very simple ideas. And that should give you the tools. I mean, the whole point of this class is to give you the tools, and in this case, mechanics, to do something new, something that hasn't been done before. To be quite honest, I doubt ever in your lifetime, your working career, will you calculate that airplane's tension in that cord. I mean, it's just knowing the tension on a airplane tethered by a cord is really not the point. Not at all. Airplanes are going to be all remote control, and even if you work for a toy company and you're designing those, you probably won't be doing it with a tether, okay? The point is, could you do something new, something different, something that hasn't done before, okay? Can you be innovative? Can you see the different patterns that are going on? It's the difference really between, just okay designs and really thriving and doing something new and doing something creative and what can be done that's never been done before. If all you can do is open up a book and go back, I'll just look up the equations, then you can only do something that has been done before. You can't do the new, the inventive, the whole idea here. So that's the idea here, and I think you're getting that. I've been saying it for a long time, and we're not going to really learn a whole lot of principles here. I mentioned this in 102. We really just learned 6 things this semester. The first one is Newton's 3 laws of motion, and then the conservation of energy, conservation of momentum, and conservation of angular momentum. And that's it. That's all we do for 14 weeks. I mean, how hard can that be? And you get 5 units for it. I mean, come on. 6 sentences, 5 units? Wow. But of course, you see what the hard part is. The hard part is that deductive reasoning, to take, okay, those simple principles and apply it to this case that I've never done before, or this case, and this case, and this case, and all the tens of thousands, maybe hundreds of thousands of new problems. Well, that's kind of my intermission, if you will. So we did Newton's laws, okay? Now, second half, 7 and 8, they go together. It's to introduce you to conservation of energy. And maybe I shouldn't say introduce, because you already are familiar from Physics 102 about the principle of conservation of energy. But that's where this is headed, and how we would use it. And how we would use it now with calculus here. And so chapter 7 is titled Work and Energy. And it starts off with the definition of work. And it simply says this. And maybe I'll just spell it out. It may take a little while, but it's probably worth it here. It says the work done by a constant force. So we don't even have a varying force at this point, but that will change. And that will be part of the lesson here. But the work done by a constant force is defined as what? Well, it's a product. We're going to multiply two things. The product of the component of the force in the direction of the displacement. There's a lot of words right there. And what's the other factor? And the magnitude of this displacement, or distance, if you will. Okay. And so let's see if I can underline these here. What are we doing? Well, we're calculating work. All right. So I'll put a big W. Work. What is work? Well, it's a product. All right. So I'm going to be multiplying two things. What are the two things I am multiplying? Yeah, did you catch that? It's the component of the force in the direction of the displacement. That is one factor right there. A lot of words. The second one is a little easier. It is the magnitude of the displacement. In 102, you just said, oh, it's force times distance. But we went a little further. Is it just any force, any distance? No, it's the component of it. Watch, let's see if I can draw a picture here before I finish the equation here. If I came over here and said, all right, here is a box sitting on the ground. And I come along and I grab that box and I pull with some force F at some angle theta from the horizontal, and I drag it across the ground, and so it moves some distance r vector. Right? So some force, some distance. How do I get the work? Is it just simply force times distance? No. I need to say right here that it is how much of the force, the component of the force, that is in the direction of the displacement. How do I get the component of the force in the direction? Yeah, so it'd be F cosine theta. That's what that sentence says. Then times R, right? And so that is the component of the force. How much force is in the direction of the movement, then multiplied by the movement. So be careful if you just say force times distance. And we often do, and hopefully you will know what I mean when I say it. I don't mean just take the force, multiply by the distance. I really mean the component of the force. And that much I think you know, because that's what we really emphasized in 102, how much of this is in that direction. But that's our basic definition of work. Now it's going to get more advanced than that in just a second here. In fact, let's continue on here a little bit. Let's add to this. I mean, if I really did hook up this block and I pulled it across the floor, would that be the only force? Aren't there other forces here? Shall we draw this a little better? I mean, what other forces are going on here?
Friction, gravity, momentum.
Yeah, I see 4 forces here. There is, of course, the one I apply. But as somebody said here, there's a normal force. There's another gravitational force. And then there is the kinetic friction as it slides across the floor here. You might even say there's air resistance, but let's just, okay, that, you know, you get the idea here that there's a bunch of other forces here. So when I say calculate the work, I need to be a little more specific. Which force? Which work? Aren't there 4 forces? So couldn't I really be saying this? Tell me how much work is done by me? How much work is done by the normal force? How much work is done by gravity? How much work is done by... So you see how this really becomes 4 questions, right? There's 4 different works and then 4 different questions. So again, starting with this basic idea of what is work, we're going to lead up to conservation of energy here and the power and the usefulness of it here. So calculating the work done by me, that's what we already said, right? We already said this would be force times the cosine of the angle times the distance it moved. Fair enough? How about the normal force? How much work is done by that one? Do you see 0? Yeah, why 0? Right, there's no component in the direction it moved. This moved only horizontal. So how much of the normal force is horizontal? None. Right? Now, if you prefer, I guess you could write this as normal force times cosine of 90 degrees times r. But isn't that 0? Right? So you're right, it's 0. As it should be. Right? How about the gravitational force? Yeah, it's really 0 for kind of the same reason. You could say it's mg, but then the mg is in a direction down and the movement is horizontal, so the angle is 90 degrees, so we get 0 work from there. So there's no work done by gravity in this case, and there's no work done by the normal force in this case. It looks like there's some work done by my hand. How about the frictional force? Any work done there? Yeah. And it would be a little different. What would the angle be? Yeah, do you see the distance is positive, but the force is negative? So if you put a positive and a negative together, what do you get? Yeah, you get a negative when you multiply those two here. So this is really negative force of friction times distance. If you prefer, you can write it as force of friction times cosine of 180 degrees times distance. Of course, that is a negative force of friction. In fact, what I really wanted to begin you to see here is when would you get positive work and when would you get negative work and when would you get 0 work? Start with the 0. When are you going to get 0 work? Right. If you have force that is perpendicular to the movement, that means this cosine angle is 90 degrees. That means you're going to get 0. Let me draw a picture for you that we saw in the last couple of or chapters, if a ball was moving this way and you applied a force in that direction, what would that force do? Okay, all forces are going to make it accelerate. More specifically. Okay, so it's going to make it go faster, is what I'm after here. Anytime you put a force in the direction it's moving, it is going to make it go faster. It's always going to make it accelerate, but in this case the acceleration is go faster. The same could be said if the ball was headed in the other direction and then you applied a force in that direction. What's that going to do to it? It's going to make it go faster again. Now, you may call this a negative force and a negative acceleration, but that's fine. It's already moving in the negative direction. So its speed just becomes more and more negative. This becomes more and more positive. But either way, I would say it becomes faster, 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 faster. Now when it comes to talking about the work, how would you describe the work? What would you say about a force that is in the direction it's moved? Would you get a positive amount of work, a zero amount of work, a negative amount of work? Wouldn't this come out to be greater than zero? Wouldn't you have an angle less than 90 degrees? And so if you pull on something in the direction it's moving, like this one, if that angle is less than 90 degrees, isn't it positive? And so you get positive work. And that's what I'm trying to point out here, that a work that is positive corresponds with something going faster. Isn't that true here too? Isn't that a positive work? Because the force would be in the negative direction, but the distance would be negative. What happens when you multiply two negatives together? You get a positive. And so recognizing what we've done in the past and correlating with what we're going to do now, I think is very powerful. And that's what I want you to see here, that anytime you put a force in the direction an object is moving, that means it's going faster in terms of dynamics, and in terms of energy, it means you've done positive work. What do you think would happen in the reverse of this? What if I applied a force opposite to the direction it is moving? What is this force going to do? It's going to make it go slower. Sure. Now, granted, it's going to be an acceleration, but the acceleration here is slower. So if the object was already going positive and you gave it a negative force, a negative acceleration, that means slow down. Now, if you gave it a negative velocity and a positive force, then that means you go from a large negative, say negative 10, down to negative 9, negative 8, negative 7. Again, you're slowing down. So forces that are in the opposite direction slow it down, right? And in terms of work, what would we say? What kind of work would we get here? Isn't it less than zero? Less than zero? And I think that's what you see here, right? The work that is negative, the reason it comes out to be negative is because the angle is greater than 90 degrees. It's, from where it's moving. You are pulling it the opposite of the direction it is moving. You are slowing it down, in other words. And so notice that positive work means it goes faster, negative work means it goes slower. Fair enough? What does zero work mean? No movement? No displacement? How much work was done by gravity? Zero. Did we have a displacement? Okay, I see what you're saying. No displacement in the y direction. Yes, but it did move, didn't it? Yeah. So zero work doesn't mean it's sitting still, right? Zero work means that the force is perpendicular to the direction it is moving. So how could I get zero work in this case, or that case, I guess? What would that force do? How much work would be done? Yeah, so zero work would be when I pull on it perpendicular. And what happens when I pull on something perpendicular? What did we just come up with in this last chapter? It turns. Yeah. And so it made it turn. It did not make it go faster and slower. So a force that is perpendicular to the motion left it at the same speed. It just made it go in a circle. Sure. Didn't change its speed though. And so the work is zero. It doesn't go faster, it doesn't go slower. And so that's the whole idea. Tie these together. Tie chapters 5 and 6 together here with 7 and 8, and we'll begin to see slower, faster, turning is the same as slower, zero, negative work, faster, positive work, turning, zero work. Right? Same thing here. If I were to pull this way on the object, that would make it turn. Doesn't make it go faster, doesn't make it go slower, and the amount of work is zero. And so that's kind of what we see here in this very simple example. We see me pulling on it doing positive work. If that's all there was, if it was just me pulling on it, this thing would go faster. If there was just friction on it, this thing would go slower, negative work. Okay? If there were just forces perpendicular to it, it would be no work. In this case, it doesn't turn because we've got one trying to turn it up and one trying to turn it down. Okay, so that the total there is a straight line, but it's still zero work. And if we were to add all these together, we might call this the total work or the net work. And now we can begin to say, I've got a positive, a zero, and a negative. Does that total come out to be positive? And if it does, what does it tell me? It tells me it's going to go faster. It tells me this is bigger than that. Which is really saying frictional force less than the component of my horizontal force, which, going back to chapter 5, we know that. We get an acceleration if the component of my force is greater than the frictional force. This would have an acceleration going faster and faster and faster. On the other hand, if this one is bigger than that one, then this thing's going to have a frictional force greater. It's going to have an acceleration that is slowing it down, and it's going to have a negative work. This number is going to be more negative than that number is positive. And so that is our first step. What is work and why do we care about it? How is it interesting? How is it going to serve a purpose? And there it is. Could it give us speed from calculating work? Yes. And so let me add to a picture that you've been watching me develop. Position, velocity, acceleration. Could you go from one to the other? Wasn't that what chapters 1, 2, 3, and 4 were all about, that first test? Position, velocity, acceleration, how are they all related? All those derivatives and integrals connecting them. Then, after we did this, and maybe I'll just put a little circle around it here. This is chapters 1 through 4. That was our beginning part, our kinematics. Now we've got into our dynamics here. We got into Newton's second law, and we said, well, how do you get an acceleration? Well, an acceleration you get from a net force. How do you get a net force? You got that by adding up all the forces. So we added all the forces. From that we got net force. From net force we got acceleration. And so that's what we've been studying then for these last two chapters. Chapters 5 and chapter 6. And now we're beginning to see something a little bit new and a little bit different. They don't fit this nice linear pattern anymore. We're not going beyond force here. What we are saying here is if you think about work and energy, that can get you to velocity. It's another way of getting to velocity. It's another way of approaching the problem. Maybe a way that is easier than the other way. Or maybe one is possible and one is not possible. And so we got to kind of look at the problem here and say, okay, how am I going to get to the final speed of this box? And in this case, if I can get the final speed by looking at how much work has been done on it. Is it positive, going faster? Is it negative, it's going slower? And for that matter, we're going to see that this is a nice way to get to forces also. And so we can use energy to get to forces, or we can use forces to get to energy, or we can use energy to get to velocity, or velocity to get to energy, or acceleration to get to velocity to get to energy to get to forces, which gives us acceleration and velocity back to position. Oh, it's going to be a fun puzzle, right? And so our knowledge is getting bigger, and the types of problems we can handle and deal with are growing in the same complex pattern that this diagram is going to grow. And of course, we are only 7 weeks into the semester, so we've got, what, another 7, 8 to go. So we'll double this picture, and then next semester we'll double that, and then the next semester we'll double that. So after a year of this, or 3 semesters, we'll be doing some tough problems. We'll build a car. We'll look at the aerodynamics and the movement of the car. We'll burn the gas and look at the thermodynamics of the energy being transferred to the car. We will deal with the optics and the light emitted from the display. And so a car is a really good example of all the pieces of physics that we go on in this year and a half of what's going on there between the optics and the thermodynamics and the motions and the flow of fluid as the transmission fluid works through the tubing, shifting the gears, and it's going to be quite fun. So anyways, this is where we are so far. All right, and so that's what I'm trying to start out here is, do you see kind of this big picture? And so this is as big as this diagram is going to get between now and the next test here. 5 and 6 chapters, 7 and 8 right there. Okay, work and energy. Momentum's coming next, by the way. Rotations after that. All right, so back to this problem then. I had said if you added all this together, you would call this the net work, right? I mean, it would look something like this. You would say it is the first force actually, let me not write anything out quite yet. Get ahead of myself, and I might confuse you. But the big picture is, you see how the work then is going to give me the positives and the negatives. All right, fair enough. Now, let me pause for a moment and do some mathematics. I'll call it a little math review, although it might be, and I'll leave those up there, it might be actually new mathematics for some of you. But I'm thinking not too many when I've asked in the past here. Let me look at what is called a dot product. Ever heard that word, dot product? Yes. Or scalar product is what your author calls it, which really is probably a better word. I just have a hard time remembering scalar product, because I learned it as dot product, and it is represented with a dot, and it's just, that's why I think about it. But I like the scalar product because it's what it gives you. Let me say this.
Somebody's in trouble.
What did, if you remember when we dealt with vectors in chapter 3, we learned how to add and subtract vectors, right? And I said a day was coming where we're going to have to multiply vectors together. And I told you there are 3 ways to multiply vectors together. And so we are at that first way now. The first way is right here. It's called a dot product, or a scalar product. And that's what I want to show you here. So let's just talk math for a moment, then we'll tie it into the physics here. But if I was just talking about mathematics, if I had vector A and vector B, and I said, let's go ahead and multiply vector A times vector B. And like I said, there's different ways of doing it. So I want to be more specific here. But I think maybe you begin to see the physics. I guess I erased it here. But isn't that really what I had when I talked about work? Didn't I have two vectors? The first vector was the force, right? The next vector was the displacement, right? And so that's where we're headed. We're headed with this idea that I'm really multiplying two vectors together here, aren't I? Now, it wasn't just straight F times R, was it? It was how much of this vector, this one here, which we often call A parallel or A projected onto B, if I can again use a word from math class here, how much of the vector A is in the same direction as vector B? Multiply those two together. And so what I care about here is A cosine theta, then times B. That would be how much of vector A is in the direction of B multiplied together with B. Fair enough? And that's what we want. Isn't that the whole point here? When we multiply these two vectors together, what do we want? Well, what we want is how much of the force is in the direction of the displacement. So I don't want the whole vector F, I want a component of it. I want how much of F is projected onto R.
What are those little lines on the next day?
Oh, so we like to give it a symbol, two lines that are supposed to mean parallel. Yeah. As opposed to, and we won't need this till chapter 10, but what about this component of A? I would call that A perpendicular. How much of A is perpendicular to B? So more on that in future chapters. But for right now, the question is, how much of A is parallel to B? And again, making sure we don't get too far away from the physics, I'm hoping you see why I care about that. It's this statement here. F parallel to the displacement. Okay? So, here's how we write it in mathematical symbols. We say, take vector A, dot it with vector B. Okay? And that's why we call it a dot product. You represent it as two vectors being multiplied together. But it's not as simple as magnitude of A times magnitude of B. It is really the magnitude of A times the cosine of the angle between them times the magnitude of B. And I think when you write it as a dot product, it's easy to forget that there is cosine of the angle between them. But in many physical properties, that's important, and work is one of them, and that's why we are going to use this idea of a vector notation here as a what we'll call a scalar product, because you start with two vectors, and we call it dot product because we represent it with a dot. We also call it a scalar product because when you multiply these two together, when you're all done, do you have a vector anymore? No, you just have a scalar. You just have a regular, every ordinary day number. And hence, that's why I think scalar product is probably a better name for it, because it tells you what do you get. Whereas, as those of you who might already know, in a couple of chapters, we're going to have what's called a vector product, or a cross product. We'll represent it with a cross, but it gives us a vector. So those are the two ways we'll care about multiplying vectors. You either multiply them together and get a scalar, or you multiply them together and you get a vector. This is not that one, that's coming up, but this is the one for this chapter, okay? And so that's all the math will do. We don't need to do the other products until we need them, which will happen later on here. But for right now, this is what we need. So this is my dot product, all right? So what does that mean? Well, that means over here, I can rearrange this definition and write it as F net dot R. Or I could write it as work from one of them is the force from one of them dot the displacement of that, right? And so that's how we're going to represent it. We're going to represent it with just a simple dot product. Okay? Now, keeping in mind that that's a dot product, there's another way of looking at a dot product that will also be very useful to us. This is one way that says, look, A times the cosine of the angle times B. That's very useful. But another way that's very useful is this. What if we take A and we write A with its I hat and j hat components? Because that's really what vector A and B mean, right? It means it's got an x and a y component and an x and a y component. Now if you multiply this out, you might remember your old FOIL rule, right? You got to multiply all four of them. You would get like ax I hat dotted with bx j hat. That would kind of be the first one. So there's our F in our FOIL. O means what? Outer components. So that outer one gets multiplied together. ax I hat plus by j hat. The I in FOIL means the inner pieces. So I'll put the inner ones together. ay j hat dotted with bx I hat. And then finally the L for last would mean multiply that times that. So this will be my ay j hat dotted with by j hat. Some of you guys look at me crazy when I said FOIL. Do you not learn it that way anymore?
Yeah.
Yeah? Oh, okay. Okay. All right. So it's kind of a nice way to remember it. But I also, it's just the distributive property twice. Do this multiplied by each one. Do this multiplied by each one, right? That's what it means there, distribute it. Okay? Now, look at this. This actually simplifies really nice. These two are both in the x direction, right? So when you say how much of this one is in the same direction of that one, isn't it both of them? So it's just ax times bx. This is nice because how much of the y direction is in the x direction? None. 0. Again, same thing. How much of the y direction is in the x direction? 0. And then how much of the y direction is in the y direction? Yeah. All of it. So when you write it out this way, you don't worry about the angles between them. And so my point is that we're going to use either one, depending on which one is the most convenient for us. And so keep this in mind as we do our mathematics, that when you take two vectors, A dot B, you can write it as AB cosine theta. If I switch the order, is that okay a little bit there? I'll put the two magnitudes first. So magnitude of A, magnitude of B times the angle. So if you know it in polar coordinates, this is really nice, right? Magnitude of the first, magnitude of the second, angle between them. But if you know it in rectangular coordinates, then this is really nice. So that is also equal to ax bx plus ay by. So your choice, and of course that kind of depends on the problem and what you're given. If you're given the Cartesian coordinates of it, you probably want to take a dot product this way. If you are given magnitude and directions, you probably want to do that way. If you're given some mixture of the two, well, then you have to figure out how much of one is the other, and it's a little harder of a problem. But both of those are a dot product. They would give you the same number.
How did you get 0 for ax? I have to.
Well,
That's supposed to be a multiple.
I mean, how
how'd this one go to 0?
Yeah, both of them, because both of those are 0.
Yeah, both of these went to 0 because this one is saying x direction. Oh, that's supposed to be a times. That's what you were saying. And then this is the y direction. So how much of this one is in the same direction as that one? None. 0. And so that's what's meant here by the dot product. How much of one is in the same direction? How much of one is projected onto the other? If you prefer, you could write this as AX times BY times cosine of 90 degrees. Cosine of 90 degrees is 0. Okay, so that's a 0 and that's a 0. Whereas this would be AX BX cosine of 0 degrees. Cosine of 0 degrees is 1, so you just get AX. Okay? And so my point is this, in this little math review, if you haven't seen this math before or if it's been a while, is we are going to take advantage of this mathematics. It's going to be very useful as we do our dot products. As we do our work and our energy, we will use dot products. And dot products are just kind of a nice fancy way of saying I'm going to multiply two vectors together. And what I care about is not really the two magnitudes, but how much of one vector is projected onto the other, then multiply those two together. And that's what this mathematics does. And we've got two really nice formulas. One in terms of polar coordinates, one in terms of Cartesian coordinates. So depending on which one we know is the one we will use to solve the problem. And sometimes it will be this way, and sometimes it will be that way. Probably most of the time it'll be this way. That's kind of how we always think in a beginning physics class. We always think about magnitude and direction, magnitude and direction, magnitude and direction. So we're always thinking in terms of polar coordinates. Not always, but certainly in part. All right, well, so far you can see, maybe you can see that I have not done any calculus yet, right? Question?
Yeah, so when you're multiplying a vector, why are you multiplying rather than adding the components of the vectors? Like, why are you multiplying A times B rather than adding A times B?
There's two parts. Why would I multiply instead of I add? It can't really be answered in terms of math.
Right.
That's answered in terms of the application of the math. What do I want from these two vectors?
Are we going to go over that?
Well, okay, and I am. The application here is, what's my definition of work? Force times distance, right? So there I want to multiply, not add. Period. Okay, that's the definition. Now, I suppose your questions can go a little deeper. Why do you want to multiply force and distance together? And I hope to answer that soon. Maybe not today, but soon, of why we want to multiply. But without saying why I want to multiply, I do want to say that the definition of work is force times distance. Those are two vectors. So therefore, I want some mathematics that multiplies them, not adds them. Okay. And we already learned the mathematics of adding them. So I know how to add vectors already. I know how to subtract vectors. Now I know how to multiply them. At least one way I know how to multiply them. And more to come. Okay. All right. So there's quote unquote my math review. It's obviously not a complete discussion on this, but it's enough for us. And so it changes our equation of work to look a little more sophisticated. Okay? It has a dot product. It has vectors in it. It allows us to move in multiple dimensions. In fact, let's try this again. Remember that block we had? Let's say that this block, as I pulled it, not only moved in the x direction, but it also moved in the y direction. How much work would have been done? How would I calculate it? And so we're back to this block. Here's the block. And so now I'm going to say pull in this direction, but say it moves in that direction. So this is F and this is R. How much work did I do? Yeah, well, hopefully you see both cases. It always equals F dot R. If this is some angle between them, theta, probably the easiest way is F times R times cosine of the angle between them. And notice I tell you the force, I tell you the distance, I tell you the angles. Just use the first definition. But wouldn't there be another option here? Wouldn't it also be how much force in the x direction times how far did it move in the x direction? And how much force did you apply in the y direction added to How much distance did you move in the y direction? So as we get into multiple movements, x and y, you can see that our whole idea of work just gets extended from one-dimensional motion to two-dimensional motion. We can say that we get a certain amount of work because it moved in the x direction. So this is the amount of force in the x direction. This is how far it moved in the x direction. Add to that, how much force did you apply in the y direction, and then how much did it move in the y direction? That's what this definition will give us. But I got to admit, if they give me magnitude direction, I'm going for this one. Right? I don't worry about components and that. So I like that one usually a lot better, but this one is just as valid. And what I wanted you to see here in this example is that there would be a certain amount of work associated with the movement in the x, and there'd be a certain amount of work associated with the movement in the y, and the total work then is the two together. Well, let me go one step further. What if, in addition to it moving x and y, so we'll keep that into the mix here, as I pull on it, I vary my force. What are you going to do there? What if I pull it with just a little bit, then a lot more, then less, then a lot more? What's going to be the work now? And so okay, so go down that road. What about instantaneous force? Okay, so maybe I'll draw a graph if that will help you think about it. Maybe it'll look something like this. Maybe the force I'm pulling in the x direction. And let's just talk about x. We can add y here in a second. But let's say the force that I'm pulling in the x direction, as I move along in the x direction, let's say I start off with a little bit of force and I pull harder and harder in the x direction. So I do a little bit of pulling and I pull more, all right? I really get into it. I'm going to really pull on this. And I get over to here and I get tired. So I go, okay, hey, that was fun, but now it's tiring. And then I realize I'm almost to the place I want to go, and I go, if I just put in one more quick effort, I can get where I want. And so now I stop at that point. And so I have a varying force. How much work? How do I calculate the work here? Yeah, and I'm going to ask you to put your calculus together. And more than that, we're going to put the calculus together, come up with an integral, all on our own. And I'm going to ask you, could you have done this without me giving you the equation? I mean, how would you figure out the work here? And here's the logic that Newton would use. Here's the logic that somebody with calculus would do. They would say, well, you know what? What I've learned is that if I had a force in the x direction and I moved a short distance in the x direction, the force may vary just a little bit, but if I take a smaller and smaller distance, wouldn't, in the limit that distance gets smaller and smaller and smaller, wouldn't that be, wouldn't that be a relatively constant force? So what I could say here is then in the limit that the x goes to a smaller distance, this would be a small amount of work. Now that's only the work from, say, here to here. Couldn't I do the same thing at the next place, and the next place, and the next place? And so if I got the force at each location and I multiplied by the distance it moved and added them all together, wouldn't that give me the total work? So what you're really telling me here is the total amount of work here is going to be the summation of a bunch of little pieces of work, right? The work I did here, plus the work I did here, plus the work I did there. And the summation of the limits as delta x goes to 0 of f of x dx is really what I'm talking about, right? I am talking about taking the force right here and move a small distance. Add that to the force here in a small distance. Add that to force times distance. Add that to force times distance. Does that make sense? Wouldn't that be the logic? A little bit of work, plus a little bit of work, plus a little bit of work. And look what we get. You ever seen that equation before? I hope so. What's that? That's the definition of an integral. That's why it was developed, right? It's the whole reason we use this crazy looking S. Because it means what? Summation. Add it all together, right? And so this is your, what, your second fundamental definition of calculus, or second fundamental definition theorem, something here, but it's a definition of what an integral is, all right? And so don't miss that, okay? Because we've done so far really derivatives. I mean, really we've done derivatives which are quotients, right? They are a delta x over a delta t, let's say, in the limit that the time gets going to 0. And that is why, you know, Newton was kind of forced to figure out calculus, or, you know, discover calculus. I like better than develop calculus. It's discovered. It's realized this is how the world works, and the time's got to be shorter and shorter. And same thing here. This is the opposite of that. You are adding them all together, and so this is a summation. So this would look like what? F of x dx, right? And so when we have a varying force, we can solve this with an integral. And that, of course, is something we did not do in Physics 102. It was, you know, non-calculus based course. So we calculated works, and we always did the easy cases. We always did, what if it was a constant force? This is not a constant force. What if I had done the y direction also? So what do you think is going to come out here for the y direction? Wouldn't it be that? How much force do I have in the y direction times little displacements in the y direction? And I'll go you one better. How can we write that? How can we write that a little bit nicer? Doesn't that look like a dot product? Doesn't that really look like the integral of fx dx plus fy dy? And doesn't that really look like the integral of the force F dotted with a dr, a movement, where dr represents a dx in the I hat plus a dy in the j hat? Yay! All right, so a lot of new math here, right? With this whole idea that we got to the main point before today, good. And that main point was, let's look at this big fancy equation for work. And here's what we have. Work, then, is the integral of f dot dr. And so that's how we're going to calculate our work. If f is a constant, oh, I love integrals with constant. They're so easy. What do? I pull it out, and I get an integral of dr, which is just r. And so we're back to the old school, no calculus type of calculations, right? The ones we did in 102, the ones we got started, right? But this is what I wanted you to see. But I also wanted you to see something different. Don't really expect it this semester, but by next semester, oh, you got to develop this skill. Could you have come up with this integral equation from just the statement that work is the product of the component of the force in the direction of the displacement and the displacement? Because you start with a constant, then you take it to a microscopic distance, you take the limit, you add up all of those, realizing that's part of the calculus. So could you come up with this equation on your own? And that's a skill I'll keep asking as the semester goes along. Because one thing that you will discover, I don't mean to scare anybody quite yet, but when we come back to school next fall, And when we get started in Physics 122, we start right in the middle of the book, chapter 23, and it expects you to know how to do this. It is not like the start of this class. There's no fuzzy, warm, easy first chapter. It is hello and welcome back. It is a hard chapter. We're right in the center of the book, one of the hardest chapters of the semester. But it will expect you to have developed this skill this semester. So we'll keep talking about it as the semester goes along. So, well, obviously we'll finish here and I'll see you.
Should I be scared if I were not to figure it out?